Center of mass is a concept that can take very complex ideas and boil them down for us. In fact, that's kind of the point of the center of mass. Imagine a wrench here, like I have in this picture, and the mass is distributed all around it. Center of mass is where if we took all of the mass of the wrench and we boiled it all down to one point, that's the center of mass. It's where all the mass could be located as if the wrench was just a single dot. Now, that's a very important idea because having the center of mass and being able to boil it down to a point mass, because sometimes things like wrenches have very odd behaviors when you throw them. But if you were to trace the center of mass, you would get a very logical, very neat, very orderly result, one that's easy to calculate. This would actually be a very good time for you to pause the video. There's a link right underneath this for a video demo of how the center of mass makes things a lot more orderly. Now, to use this to our advantage after you've watched the video, to use this beautiful example to our advantage of center of mass, we're going to have to be able to locate the center of mass. Once again, let me actually somewhat formally define this. Center of mass is the location where you could boil all of the mass, the total mass of an entire object or system, down to one location, and that location will behave like the entire object would if it was a point mass. Now, finding the center of mass on some objects, let's say a uniform rod, is very easy. It's just going to be right in the center. Or it's not even overly hard. If you maybe add a rock to somewhere over here, you could figure out the center of mass of a uniform rod is there in the center, and then you know the rock is going to kind of weight the actual center of mass of the entire system maybe a little bit to the right. So that would be the center of mass of this rod, and here's the center of mass of that rod. And whenever I say rod, I really should mean entire system for this bottom one here. And we're going to actually, you could calculate this out using this equation. You would figure out where you would boil everything down for the rod to its center of mass and treat the entire rod now like a point mass and the rock like a point mass, and then use that equation kind of like we're going to do in an example problem down here. But then sometimes you have to deal with something nasty like this. Maybe even the mass isn't evenly distributed in there, and it's got all sorts of funny things going on. Anytime you need to calculate the center of mass, you would use this equation, and that looks a little wacky, but let's explain it really fast. This over here just says add up all the masses. Well, that's just total mass, so it's 1 divided by the total mass. Times, this says multiply the distance and the mass together for all of them and then add them all up, which is what this is. So it's really not that big of a deal. Take the total mass, and you're going to put that down on bottom, 1 divided by, or in the denominator, and up top, or multiplied by 1 over m, you're going to take each position, let's say x1 here, and multiply by the mass at that position, m1. And then you're going to add that to position 2, however far away from 0 it is, x2, and multiply it by whatever mass is at that position, m2. And if there are more masses, you would just keep going down the line. x3, however far away it is, times m3, so forth, and so on. Add them all up, and then multiply by the 1 over the total mass. So this is a relatively simple equation to plug through. Let's work a simple example problem here. I've got 3 masses, m, 3m, and 2m, and they are located equal distance from each other, distance x. Now, I purposefully located my first mass at the 0. That's just a trick that's going to make your life a lot easier, make the math a little bit easier. Try to locate the first mass whenever you're dealing with point masses here, like we are, on the 0 point. And now we're looking for the center of mass. Now, if both of these were equal, the 2m and the m, let's say this was 2m over here, so these two were completely uniform, then quite obviously the center of mass would be right in the center, which is where the 3m is at. But that's not true. The 2m a little bit bigger than 3m, so I'm expecting my center of mass to maybe be somewhere over here, a little bit beyond x, but not all the way up to 2x. So now I go ahead and I rewrite my equation here, and I have 3 points that I have to deal with, 3 masses, 3 points, and now I'm going to start substituting in. So I add up all the masses, put the total mass after adding it all up under 1, and then I take each position and multiply it by the mass that's there. So the first one, I purposefully set at 0. That makes life a lot easier whenever you set that at 0. So 0 times m is going to come out to be 0, and then the next position is position x away, right? And that the 3m is at whatever x is away, and then my 2m is at 2x away, because they're equal distance from each other moving outwards from 0. So my total mass, adding that all up, gives me 6m, 3 plus 2, 5 plus 1, 6m. Now this completely cancels out because it's times 0, gone. This guy here is going to give me 3mx, right, because x times 3 times m, and then 4mx here. 3mx plus 4mx gives me 7mx. Notice now I have an m in the denominator, m in the numerator, so that cancels out, and I come out with something that is exactly what I predicted here. 7/6 is where the center of mass is. So I'm going to go just beyond x to the 7/6 mark is where my center of mass would be for that system of point masses. So we just completed a problem where we only did one dimension and everything was on a nice little line, and so the next logical extension is to actually go 2 dimensions. So I have 3 masses here at these coordinates 0, 0, and 2, 0, and then 1, 2. Now, what a problem might tell you instead is the distances between them, and then you actually set them up. And like I said in the previous problem, it's a lot easier if you'll set one of your masses at the 0 point. And so in this problem, let's find the center of mass for these masses. Now, this would actually be an isosceles triangle here, and the masses are not all the same. I have 2 masses at the bottom that are 2m and 1 mass at the top that is 4m. Anytime you're doing 2-dimensional problems, just like any other 2-dimensional physics problem, you're going to divide everything into components, into an x and a y component. And thankfully, in these type of problems, dividing into components is relatively easy because they're going to report them in standard notation here where you already have an x and a y coordinate to substitute in for your x and your y's. So let's go ahead and let's solve for the x center of mass. So substituting in here, total mass is 8m, 2 plus 2 plus 4 is 8m, and now then I substituted in all the lengths times the mass. The first mass, 2m, is located at 0x. I called this the second mass up here, and it's located at 1x, 4m at 1x, and then at 2x I have another 2m, and now this is just simple solving. Once again, 0 times anything cancels out, so then I end up with 4m, and 2 times 2m, 4m again. And I come out with the center of mass in the x-axis at 1, which is exactly what we'd expect out of an isosceles triangle. It's symmetrical in the x-axis here. So the center of mass is going to fall somewhere along this line here at x equals 1. So now we need to solve for the y to see how high up or how far down it is. And we're kind of expecting it to fall a little bit higher up because of the second mass up here, 4m, is a little bit heavier, a little bit bigger, so it should maybe pull the center of mass upwards a little bit. Notice here in this problem we actually have 2 things where they are at 0 in the y-axis, leaving me just with only this middle point that actually has a y-axis point to deal with, 2 times 4. We come out with a y center of mass of 1 also whenever we actually work all that through, which does actually make sense. Yes, the 4 wants to pull it up, but it's having to fight 2 others. It's having to fight 2 other 2m's down on bottom. Notice how the up and down mass is actually distributed evenly. 4m on the 0 and then 4m up here at the 2 in the y-axis, which is going to give you a center mass of 1. So the actual center of mass, if we were to plot this, would be 1, 1. So that's a simple example of a 2-dimensional problem, and this time I chose to use actual numbers in there instead of variables, but variables x and y would have worked just fine, just like in the previous 1-dimensional problem. All right, so now you're going to work a few problems with those in class, and then we're also going to go into actual objects, thin rods being specific, where the mass will change and density will change as we go, so we'll have to use a little bit of calculus for that.